Now in this lesson we're going to take a look at sum and difference of cubes, and this is very similar to the difference of squares problems that we were doing earlier, but this time we're looking at either the addition or difference of cubes. And if you're looking at these formulas, they're exactly the same over here on the right. The only difference between them is the signs. Notice the x's are in the same place, the y's are in the same place, the x squareds, the xy's, and the y squareds are all in the same place. The only difference is the signs. This one is positive, this one's negative, positive, and these two are both positive. And there's actually an acronym that goes with this, because I have students usually memorize these equations, and then because they're both the same, they only have to know that this acronym, which is SOAP. And SOAP stands for same sign, opposite sign, always positive. What that means is this front sign, if it's positive, this sign in the first one will be the same, the next one will be opposite, and then this one is always positive for both equations. So you can see that here. This one's negative, the next one's opposite, and then this one's always positive. But the nice thing about the online course is that you don't have to memorize the formula, you just get to write them down. So the key is to still recognize when you actually have a difference or sum of cubes problem. So, for example, I could have a to the third minus 8. Now, a to the third minus 8, I have to recognize that there's a cube root for both of these, which means I could take the cube root or ask myself what to the third power is a to the third, and that's just a. What to the third power, or what's the cube root of 8, and that's 2. So this a to the third power and 2 to the third power. Now these are difference. This is a difference problem, which means I'm using the second formula. So all I have to do is replace the first number where all the x's are and the second number where all the y's are, which means the first number is a minus the second number is 2. So that's where all the x and y went. And then the next step is to put the a to the second power plus xy, which would look like a times 2, but I'd like to see 2 times a, so I rearrange them. So in other words, you put the y first and the x. Doesn't matter, it's just multiplication, you can flip it either way. And then finally I put plus the second number squared, so 2 squared, which is 4. And this is your final outcome for this factoring of difference of cubes. So let's do another one. Now in this problem you'll see that I have the sum of two cubes. If you recognize that the cube root of 27 is 3, and then x to the third power. And then I have plus 64, the cube root of that is 4 cubed. And so now I just replace the x's and y's with the first number and the second number. So the first number is 3x, so I write 3x minus the second number is 4. And then I write the second parentheses, it's going to be 3x parentheses squared, and I write that for a reason because I have a lot of mistakes. We'll work that out in a second. And then plus 3x times 4. And finally, plus, oh I'm sorry, I put the signs wrong. This one's a plus sign, so this should be a plus. The second one should be a minus sign. And finally, thirdly, I should have plus the 4 squared. Okay? So now I just work that out to simplify, and I should get 3x plus 4 times 3x squared, which was 9x, minus 3x times 4, which should be minus 12x. Sorry, this should be 9x squared. And then plus 4 squared, which should be plus 16. And so that's your final outcome for the factoring of this sum of cubes formula. So now notice again the difference was I had the plus sign, so the signs changed throughout here, and then there was a number in front this time, so I had to cube root it to get the following numbers. The x's were all had an extra number in front of them. Now I'm going to show you a problem that doesn't at the beginning look like a sum or difference of cubes problem, but it actually is, because I could take the cube root of a to the 6th and it would give me a squared, because a squared times a squared times a squared is a to the 6th. And then 1, most of my students see 1 and they don't think that the cube root of 1 is anything. Well, it does actually have a cube root. The cube root of 1 is 1. So what that means is a squared to the third minus 1 to the third is this a to the sixth minus 1. So this is actually the difference of cubes. So we can actually factor this to be a squared minus 1 times a squared squared. I know that's weird, but a squared squared plus a squared times 1, which is just a squared, plus 1 squared. Now, this problem is going to get a little bit complicated because I'm going to get my answer here for this part, which would be a to the fourth. So this is a to the fourth plus a squared plus 1, which is fine because you don't need this square, it's just 1 squared, which is 1. But this beginning part, a squared minus 1, is actually the difference of squares. So this solution just got a little bit more complicated. So I went ahead and rewrote it so that we could have some more space here. And you can see I have my a to the fourth, a squared, and the 1. That part didn't change. This didn't change either, but I need it to because this is really the difference of squares. So that means it factors to be a plus 1 times a minus 1. And then the second parentheses just comes down a to the fourth plus a squared plus 1. And now that's as far as you can factor. So there are some problems with these difference of cubes where you can't actually factor a second time to go ahead and to get a more factored answer. Now for my last example, I'm going to do one that's looking seemingly very complicated at the beginning, but I just need to work through the fact that, in fact, let's make this a sum problem because I've done two different ones. I got 125x to the 12th. I need to think through what's the cube root of 125, and that's 5. And then the cube root of x to the 12th really means what's 12 divided by 3, and you get x to the 4th power. Plus, so this is cubed, plus 27 has a cube root, which is 3. Y to the 6th we worked out earlier, or x to the 6th is what we had earlier, but y turns into y squared to the 3rd power. Okay, so now this is a sum of cubes, even though it didn't really look like it at the beginning. If the exponent is divisible by 3, it is in fact a cube. Okay, so now this works out to be, we use the sum formula on top, 5x to the 4th plus 3y squared times 5x to the 4th squared minus 5x to the 4th times 3y squared plus y squared, 3y squared squared. Now, once I wrote it all out, I actually need to simplify it. So the answer is going to be 5x to the 4th plus 3y squared times 5x to the 4th squared is going to turn out to be 25x to the 8th, because what you do with the 4 and the 2 is you multiply them to get the 8, minus, I multiply the 5 times the 3 to get 15, and then just x to the 4th y squared, and finally I write plus, oh sorry, I should have wrote that in parentheses at the beginning, 3y squared squared, which turns into 9y to the 4th. And that's your final, disgustingly high exponent of an answer. Okay? So this is your sum and difference of cubes. You're just looking for, can you cube root the number at the beginning, and then does the variable have an exponent that's divisible by 3?